Okay, so let's start with a little bit of introduction about myself. My name is Gang Tao. I'm the CTO of a startup called Timeplus. At Timeplus, we build like real-time data processing stuff. In the past, I've been working for like Splunk, EMC, and SAP, right? I was working for AI project, big data project. Especially for the machine learning, most of my machine learning experience were when I was at Splunk. I was the principal engineer developing, there's a tool called the Machine Learning Toolkit for Splunk. Right? Some of you know Splunk, right? Yes, some of you. Okay, cool. Because Splunk is also a big data player, most in the observability domain, right? Okay, so today I'm going to talk about real-time machine learning. So what does real-time mean for machine learning, right? So actually the two dimensions you can think of. The first one is called real-time prediction. That means when your data come, you make a prediction in real time, like low latency prediction, right? Real time. The other one we say is something like an online learning. What is online learning? Like a continuous learning. Like the difference is that I explain a little bit about machine learning concept here, because not everybody know machine learning. So machine learning, what does machine learning do is actually, machine learning is like we call model, right? What is model? What actually is a model, right? Today we talk about AI quite a lot, right? The large language model, which is a model as well. So the machine learning model is actually just you can think it as a function, right? It gives you an input and get output. But this function is not written by a program. It is a program, but it's not like a function. I write the function, say, parameter A plus parameter B equals C. That's a simple function, right? That can be a model. But in machine learning, this model is actually driven by your data, right? You have a lot of data, and you put your data into this model. We call this training, right? A training process. And after training, you get a function. That function most likely we call it a predictor, right? It's actually very, very same at what the large language model is working, right? The large language model is actually, you can think it's a model with a lot of parameters, right? And you give it a lot of data and train, and then it can do complex stuff, right? So it's similar. So what is the real-time? I give another example about the real-time machine learning. You can assume maybe I am a model, right? I'm a people, right? I do want to predict my health status, right? So how do you predict my health status? In the medical research, right? You actually collect a lot of features from me, right? You can collect my height, right? My weight, or my heartbeat, or my blood pressures. All these can predict my health status, right? So that is actually this height, weight, like a heartbeat or blood pressure. All these are features. So these features can represent the state of what you are going to predict, right? So, and then here comes the real-time one, right? For example, if you want to predict my health status, which feature you want to use? Is it my height or my heartbeat? Which one is better? Heartbeat, right? So that's why the heartbeat is changing from time to time, same as blood pressure, right? These are important features for you to do. It's similar like any of those machine learning models, right? If you want to do real-time prediction, you need those real-time features, right? That's why we are talking about the real-time machine learning. So there's a lot of use cases for example, fraud detection. You want to make the fraud be detected as soon as possible, right? Instead of waiting a lot of time. So you need real-time features to detect if this fraud is fraud or not. Other case like recommendations, right? If you visit a website, they give you recommendations. Actually, there's a lot of machine learning model in a backend server, right? So they actually give you a recommendation based on your latest behaviors. What do you visit last time instead of what you visit last year? Because you're interesting, the more real-time features we have, we can predict your favorite in a better way, right? That's the recommendation. Some other case like real-time pricing, similar stuff. There are a lot of these cases. Okay, so this is a machine learning architecture. You can, like I mentioned, right? This is a very typical real-time machine learning architecture. So you can see we start with data. From left, the raw is the data. So we have a training pipeline. That is, you have offline features, right? And these features joining with the label, we got the training data. And this training data will be used to train the model. And the other is the inference pipeline under the hood, right? So you get the real-time features, we call the online features, and these features will serve, will be sending to the inference, the trained model, and then you got the result, right? This is a typical machine learning workflow. And then there's a lot of tools actually you can use. For the data, maybe today a lot of data is coming from like a Kafka here because like an integration, you have a lot of data sources. So to easily get all your data into a model, into training, we actually, most of the best practice is you put all your data into a event stream. So you get all this data. And for the offline training, you can actually use some like Flink or Apache Spark and train the data. The training data, once you transform these data, you actually save those data into like databases, like Snowflakes or S3, like historical store, right? And then you use this historical data to train the model. And for the online features, that's real-time features, and you use some other stream processing tools, and then you probably want to cache it like in Redis or something. And then you go to the inference. So that's some tools you can use. So, and here I give you some example about these features, right? For example, the features, actually we talk about the real-time features, and the feature is actually just a measurable properties or the characteristic of your data, right? So these features can represent your data when you use to train a model. So, and when we talk about real-time, actually these features are time-related, right? Because when you want to do real-time prediction, you actually want the latest fresh features. So the feature actually, but there's no good features or bad features, right? All these are features you can use. For example, the historical feature, like in my batch, you can say in a payment domain, right? You can say the daily transaction volume, right, for the past 90 days. That's a feature, right? You can calculate that features. And there's a near real-time feature like average transaction value over the past 30 minutes, something like that. And the real-time feature is that like once the transaction is coming, right? If the transaction value is bigger than some threshold, and sometimes you want to take a look at those very big transactions, right? So these are all features. You can see these features actually when we talk about time-related features, and it can span like historical features and real-time features. There's a lot of different features, right? So how do we create those features? How this feature is generated? Actually, because this is a data community, right? I think there's a lot of SQL Server, Postgres. Actually, these features can be easily generated by your SQL, right? If you have a database, say your feature could be a transformation, right? The transformation can be just change the scale, just do some ranking or do some binning. So that's transformation or aggregation, right? A lot of database is designed to do the aggregation very efficiently, like mean, max, average, like STD. All these are just the aggregation features. And there's time-related features, like time series features, like moving average, right? Like lag. And lag and shift are actually very useful in the real-time machine learning because it gives you the relationship between the time series data. The lag means the current data and the previous data, right? So that's the lag. And shift means you shift data forward, right? These are very common technologies used in the time series data analysis. And also there's some more advanced features, like today, we talk about embedding. So who of you knows like a vector database? Who of you use vectors? Right, yeah. So vector-based database is very popular today because of you are talking with large language model, right? So the embedding is actually just a vector, right? You turn your image or your language, right? You say some words, say some text, and we can turn it into a digital vectors, like a vector of stuff. And frequencies or labels, all this stuff can be, actually it's just very suitable to do with SQL, right? That's why I'm talking about if you are doing machine learning, actually SQL is a very good tool to help you to build features. Okay, so here's the paper. Somebody of you might know this woman, Hyun. She's a professor of Harvard University. She's very famous in the machine learning domain. So he provided this table, right? In one of his blog, she provided this table. Tell you most of the feature. There's a called feature platform. Right? How do you build feature? You see those big companies like LinkedIn, Airbnb. They are building their internal machine learning pipeline. They have this feature platform, right? These feature platforms are actually built with two important technology. One is we call the feature API. The feature API is actually doing those feature generation, like mentioned, the transformation, the aggregation stuff. So you can see a lot of them are SQL. Some of them use Python. Some of them use descriptive language like YAML or JSON, right? So these are because for the data scientists, they probably prefer Python. And descriptive one is more like easy to manage because it's more like if you're a data engineer, you want to operate your stuff like DevOps, right? They want to describe everything in a descriptive language like YAML, right? That's more easy to manage. And there's streaming processing engine as well, like Flink, Spark, or something, like I mentioned. So when you build this stream machine learning pipeline, right, you need those streaming processing stuff. Okay, so there's really a lot of challenges here. So the challenges about real-time machine learning, at least some of those challenges, right? So the first one is feature freshness, right? Like I mentioned, if you, the same examples, like you are making a prediction model about my health, right? You need to get my real-time features, my latest blood pressures, my latest heartbeat, right? All these stuff. But not all models, not all systems can give you the real-time features, right? Because why is that? Because like I mentioned, there's aggregations. There's a lot of complex computing as well as your data sources actually came from different systems, right? Some system might running fast, some system might not, right? And you need to make all these systems work together. That's something hard. So also processing data with huge volume of data generates some latencies. The next step is consistency. So if I go back to the architecture, you can see one of the issue with this architecture is similar like in the data architecture. There's one famous architecture called the Lambda architecture. Probably some of you might know that, right? The Lambda architecture. So with Lambda architecture, you actually have a real-time decode line and a batch and the streaming one, right? So it's very similar like in the machine learning stuff. And one of the issue with Lambda architecture is actually your batching system and your real-time system are two different systems. And they don't share the code, right? For example, your batch system is developed using some Java applications, and your streaming processing is done by some Flink or totally different, right? When you change something, you have to make sure the two systems work together, right? They don't fight each other. They are consistent. The other one is backfill historical data. When you generate the features, right, you actually need to use some historical data to regenerating some new. For example, you have a new features. Previously you don't have like a 1 minute aggregation, right? You only have like 5 minutes aggregation, and you want to get a fine tune or fine granularity of data. So actually you need to replay your historical data and recalculate in a new granularity. So that's the backfill. Point in time correctness. So this is something I am going to talk about later. So, but that means your data, your feature must be aligned in the time, right? You cannot leak the future. You cannot go back. You have to strictly align in the time correctness. I will have example explain that. Also, there's for most of the streaming processing system like Flink. I don't know if you guys, any of you use Flink or Spark to processing data, but generally this system is hard to manage, right? So that's the challenge if you're going to build. So that's why only those big companies like LinkedIn, like Airbnb or Uber, they build their internal streaming processing and machine learning system super complex, right? Because they have like 100 data engineer to do this, right? They can do that, but not every, question.
First of all, I have no streaming experience.
Yeah, sure. No problem, yeah.
So where in the process do you store that? Is it after the streaming or is it in a separate process?
You are talking about where data is stored, right? Yeah, that's actually a very good question. So actually, data store is depending on how you design your system. Before streaming, for example, I give you an example. The data stream came from Kafka. Actually, Kafka stores your data, right? But Kafka has a retention. That means you can set because streaming data, the problem with streaming data is actually the hot data is valuable. Like I mentioned, right? 1 hour data is very valuable. You want to check it again and again. But 1 week data, probably not. It's cold data. We don't want to keep them. And Kafka is actually keep your data on the disk. And sometimes the disk is expensive. Of course, there's some new technology to host that. But for streaming data, the problem is that actually even before you consume or process or consume this streaming data already stored there, but it has a life cycle. It has a retention. You only keep like 1 week or 2 weeks, but depending on your requirement, because more hot data you store, it costs more. Right. After processing, like you do a transformation, you use Flink or Spark, you still need to save it, the aggregated data, right? So traditionally, they actually, with big data architecture, they actually save this in some like Hadoop, HBase or something. But today, you can use more technology, like you can save it in Snowflake, you can save it as S3 or any other database, right? So you can do that. So these are different architecture options when you build your machine learning pipeline, right? There's 3 different options. The first one, it related to how your feature is calculated, right? The first one we call the in-model features. If you're familiar with deep learning, actually in deep learning you don't create features, because deep learning will learn the features in its layer. There's a lot of different layers. Actually, you can think there's an autoencoder layer, and this layer actually learn the feature. So that's actually part of the in-model feature. You don't have to do the feature, extra feature pipeline. Your model itself contains a calculation layer that calculates the features, right? And the second one is actually, like I mentioned, you have a shared computation layer. The shared computation will calculate your features for your both historical one and real-time one. So that means they share this computation. Like I mentioned, by share this computation, there's no inconsistency, right? Your real-time features and historical features are same. And they actually, like the question, right? You just asked, there's a storage here. For the historical one, we actually keep all your historical features there, because maybe later we want to build different models, right? We want to re-access these calculated features, so we need to store there. And the last one feature is actually, we call the feature store or feature platform, right? So there's a layer. The simple one is just move the storage here into this component, right? So for all your features, you just keep them. So there's a pros and cons. I'm not going to talk them in details, but if you do want to design your own machine learning pipeline, we can talk that. You can contact me. Okay, this slide talk about the point in time correctness. So point in time correctness refers to the principle that the feature used for machine learning should accurately represent the state of the world at a point in time. So if you take a look at this picture, this is a reference picture from the Chalk.ai. Chalk.ai is actually like a feature platform provider, right? You can see there's three different features: feature 1, feature 2, feature 3. They all, because the stream processing, these features are coming in real time, but they don't align each other, right? For example, at this point, you got this feature 1, and then next you got the feature 3, which is 5, and then you got the feature 2, right? It's true. And actually, when you do a machine learning training, or when you generate a feature, at this time of point, you need to find the latest alignment of the feature, right? For example, at T1, you use the feature 3 equals 5, feature 2 equals 2, and the feature 1 equals 9 as your feature, right? At T2, you actually use this 1, 2, and 9 as the second features. And you actually skip this intermediate feature because they don't align. When you run a real-time one, you only care about the latest one, and you make them alignment. So actually in SQL, there's one query can help you to do that. I don't know if any of you know which SQL you can use to do this. No? It's called as of join. I don't know if you use as of join. No? Okay, later I can share how you can use as of join. So a backfill, it's something I mentioned when you there's some missing data, right? And you want to use some historical data to backfill or recalculating something. So that's a basic introduction of the real-time features. And when you build your own machine learning pipeline or stuff, so these are the important features you probably want to use, right? First, it's a tool that should be in real time, it's consistent, right? And second, it should support both streaming and historical, like I mentioned, right? There's two parts of your, and third one in it, time travel or as of join, you can align your features using the timestamp. And last one, we probably want something that's simple and easy to use. Yes, question?
I'm just thinking what that time travel means. It's historical.
Yeah, good.
Okay, yeah, template.
Yeah, good. Yeah, that's actually very good. Yeah, because time travel is actually sometimes a little bit confusing because different people have different idea about what time travel is, right? So, like I mentioned, exactly in my context, in this real-time machine learning context, the time travel just means my system can, because time going forward, like T1, T2, T3, right? In my context, it just means I can go specific to the time 1 and find those features like 9, 2, 5 in my system using the timestamp. Right, that's what I'm doing, right? Okay, so here's the sample of the streaming SQL build features. Like I mentioned, I think a SQL system, a streaming SQL system, is actually a very good choice for you to build this machine learning model. And here's a sample, right? You can see there's some concept here. I can quick introduction, but later I can demo more. But here is we create something called a materials view. So materials view is actually just a long-running process that read your data, process your data, and save to a database table, something like that. It's continuously running. And doing some incremental processing. In my case, you can see I create a tumble window using this online payment. Later on, I can share for a 1 minute window. So in this 1 minute window, I actually count, do some aggregations. So for each account, I calculate the aggregations, like in this 1 minute window, how many transactions, right, using this count. This is easy to understand. So what's the max transaction count, what's the mean, and what's the average? And these actually just generating 1 minute feature. I call the 1 minute feature. So for each 1 minute window, you actually get this data. Okay. So in today's world, if you are looking for some stream processing tool, I list some of them. Like there are open source one, like Apache Flink, Apache Spark. And there's one Confluence called KSQLDB, which is probably you know that Confluence acquired Flink team. So there's Immerok, the Flink team. So the Confluent will prefer to use Flink. There are two Rust-based streaming database, Materialize and Rising Wave. They also provide like a materials view. You can continuously processing your data. And also Timeplus, like I'm working for Timeplus. So there's a open source database called Proton. So I'm listed here. So actually, I will show you the demo using Proton as an example, how you can actually create these real-time features used for your machine learning pipeline. So let's continue. So a little bit about Timeplus, right? Timeplus is a like streaming processing platform. So it's built on top of the Proton, in the Proton engine. So basically you use SQL to as your interface, like any other database. And it has both row and column store. And so you can build, but fundamentally the underhood is just stream processing. So you can process your data in real time. So that's a high level architecture. Like in Timeplus, we can read data from different channels. You create views, materials view, stream, and you process your data. You can send it to some downstream components. So the benefit of using such platform, like I mentioned, first, this platform using streaming processing, that means this is one of the channel to provide low latency because it processes data as soon as new data comes. And it's incrementally processed data because they keep an internal state. It doesn't recalculate it from scratch because they keep the state. So it's a way to provide real-time processing. And there's a stateful processing with TVF. TVF is actually those time window, like tumble, hopping, session. If you're processing real-time data, actually these are important because one of the challenges is streaming data is actually unbounded, right? You cannot process unbounded data because you are waiting for new data. There's always new data, right? So when you process the streaming data, you usually cut them into windows, right? The tumble window or session window or a hopping window are mostly common way to use. And so these streaming SQL system, also they are good at both streaming and historical. Because like I mentioned, the materialized view provides real-time processing and itself is built on top of a column database like ClearHouse, right? So it actually can run historical query as well. So, because it's a one database, so actually you can think it's a combination of your stream processing Flink plus your database, like ClearHouse or whatever, Snowflakes or whatever, right? Okay, so maybe I think the demo is better because I've talked a lot. Maybe a demo can better explain how it works, right? So before I start the demo, any other questions? Yes?
When you talk about aligning multiple features,
Yeah.
is that relatively trivial to get the frequency right between many different teams, or is there just sort of like a approach to get the right frequency?
Yeah, when I talk about alliance, actually in our case, in the database view, these different data, just a different stream. You have a fast stream, you have a slow stream. And in the stream processing, it just means, I don't know if you understand stream processing. There's a watermark. That means you need to wait late data. So sometimes it's complex, right? You have a 3 stream, one stream comes late, you set a watermark, you wait some time, wait some late data, and then you join them together. Because you cannot join the latest data, because some data may come later. So that's the complex part of stream processing. It's not something handled by database today, but it does handle by the stream processing system. Yeah. Okay. Okay, let me start the demo. So my demo is a use case like a fraud detection. So there's a payment stream, and you want to build some features using this real-time payment data, and then we can check what are those real-time features and how to use these real-time features to train a model or to do the inference. So this is the system architecture. Like we have online payment data, and there's a label. But in my case, I have a simulator that generates all the payment data because I cannot connect to a bank to get the data, right? It's the privacy. So I generate some sample for you. So we have a label stream, we have payment stream, and I create these features. And all these features, I have as for join here, you see, that makes it align. I have all the feature in materials view, so it continues processing all the data. And I train, with the label, we train a model. I use Caret, which is a AutoML engine. It's pretty easy to use. We train a model, and we serve this, and we use some prediction API here. In our system, we actually have a customer UDF. This UDF is actually means you can call the SQL to do the prediction, right? So that's the whole system, and I think I already start the demo system. So it's a Docker one. So it contains 3 components. This is a Timeplus. The Proton is running here, the database engine. The detector here is actually just a simulator, generating the labeled or the transaction data. And here is this is the simulator, and this is the machine learning stuff. I already trained a model, so I put this model here, hosting using the fast API, so I can call the API to do the inference in the real time. That's the architecture. I can show you the demo. So first, let me log into the system. So this is the Timeplus UI, but I just use this for a better demo, but you can do it using the open source Proton database. So there's some streams. The first stream is the payment, and the second is the label, right? The payment is just like a real time, you get all your payment data. Yeah. So this is a streaming query. If you run this, you can actually, the new data is pushing to you. It's real time. So once there's a payment, you can get it. And there are a lot of features, a lot of column in this table. We call it a stream because it's not compared to the traditional database. It's more like a fast changing one. You get always get new data into this stream. So there's the ID, there's a transfer type, like it's a transfer or it's a payment. There's an amount, account from. This actually came from, the schemas came from a cargo database, right? Cargo data set. You can generally use for some machine learning purpose. So I actually generate some fraud transactions. I cancel this query because the streaming query is actually a long-running query. If you don't stop, it continuously processing it. So, and there's a label stuff. So actually, this one is actually once there's a simulated fraud transaction, I will save this. Because this is a simulation, like it's similar like I want to verify if how good my model is, right? Also, I need to know, right, if the simulated transaction, we have 3 different type of fraud. Some are like a big amount of compared to your average transaction. Some like a lot of small transaction in a very short time, right? We think that is a fraud, right? We create some different type of fraud. I can share you. I can share you the code here about how these different transactions. I make it bigger. Countries. Fraud. Yeah. For example, the fraud type 1, it's just like a right. Let me check. Yeah, transfer very a small account like this. Sleeps 3. Yeah. Like, yeah, I think I have comments here. Transfer all followed by 001, because some fraud is just try to transfer 1 cent. And with success, it will transfer all your money. So that's one of the fraud. The other one, similar, is transfer all your money into different account. Like you have 1,000. It transfer all your money into several different accounts. So it's hard to be traced. The type 3 is just pay all money to a merchant. It's like an online fraud, right? They check how many money you have and transfer all your money to some target account. These are all very irregular behaviors, right? So we simulate this different behavior, and we want to check if the machine learning model can do it. Okay, so let's go with the query. So that's the label, right? So the next I'm going to show you some about those features. For example, let's go with the real-time features. So let's view. So the real-time features here, probably I can make it bigger. I copy this view here, so you can see better. Is it small or good? Okay, so you can see it's I have a CTE first. I actually use this lag. So the real-time feature in this case, I choose amount as choose how many transfer amount you're doing or payment, right? And the other is a lag as a previous amount, because that means that's something like time series related stuff. So every transaction, I want to reference this previous amount, right? And the previous transaction time. That means where did you do your last transaction and how many payment you did last time. So that by doing so, I actually enrich your transaction with more referenced like a lag previous features, but in real time, right? Every time I actually, by doing so, we actually provide you some reference for the history in real time. This is important for some different type of transactions, because if you if you transaction, sometimes if you have do a lot of transactions, the feature like your previous transaction type is very quick, right? That can help us to identify the fraud. So, yeah. Also, you can see we by doing so, we actually run a date diff, so we know the difference between current transaction and previous one, right? So, okay, that's the another sample is this 1 minute features, right? Let's take a look at this 1 minute feature as well. So you can think this 1 minute is the example I explained before, right? Like a 1 minute tumble window, I calculate some aggregations. So these can be used as one of my features. And like 5 minutes features, what I did is, say for 5 minutes, I count distinct account 2. This is actually very helpful when you want to check in 5 minute time window, how many different account this account transferred to, right? If this is a big number, usually it means it could be a fraud, right? So you can see how SQL is powerful to build all these different features. Actually, I also have a 1 day features here. So it's historical feature. It's more like I copy it back here. See, this is the aggregation I count. Actually, I don't, this 1 day, right? I calculate, use 1 day to aggregation, and then we do a global aggregation, say what's the average max for your daily transactions, right? By doing so, we actually give you some long-term features to know, oh, how this account behaves at the daily level, right? So by doing all this together, this comes to our materials view of this, we call the all features, right? We actually build these all features using this query. Yeah, this is a little bit big, but probably I can just direct show the underlying SQL. Yeah, maybe this is better. So, yeah, it's actually a as of drawing. So, like I mentioned, we have these different views. Maybe I just switch back to this similar, right? We actually just select all these different views, and we drawing the 1 minute drawing on the let me see, yeah, sorry. You see, actually, yeah, here. Just copy it. Yeah, here. So actually, we join the real-time features with other 1 minute feature, 5 minutes feature, 1 day feature, use as of join. So the as of join for each, because real-time features actually came for every single payment. So when you join with 1 minute, 5 minutes, 1 day features, they actually give you alignment. So for each real-time features, it gives you the latest aligned 1 minute feature, 5 minutes feature, 1 day feature. So then we actually, if you take a look at this materials view, it actually gives you for each payment, like there's ID, it actually gives you all these features, right? Account, like a previous transaction, all this stuff. It actually align them in one feature MV. And this MV can be used for training the model or do the inference in the real time. Because it's the same material view, you don't have a separate batch or streaming processing pipeline. They are combined together, like I mentioned. So, and then we can actually call this, we have an online MV called the detective fraud. So it actually, we call the fraud detection UDF. The UDF is actually, we have already a trained model running on the PY Garrett. So probably I can just run this part of the query to give a example. So you see, I select from the features, and I call this fraud detection functions. And then I actually get result, like this is a backfill. I backfill 1 hour, but to make it simple, I just backfill 1 minute. So there's fewer data. If I run this, you can see I do some real-time prediction. The 0 means it's not a anomaly. The 1 means it is an anomaly. You can see it's actually I'm calling the PY Garrett. I have a server in the backend here. So this, you can see there are a lot of like API call. For each transaction, we're actually doing real-time prediction using this UDF. Right. So here's the historical status. Like some of them are 1. Actually, there's predicted as a fraud. Some are not. But most of them are not fraud, because fraud are just a little part of them. And you can run the some of the model performance. You can, in our case, I think in this example, actually we have a very good performance, like very high. But actually the recall is not very good because most of it is just not fraud, right? Okay, that's mostly my demo, and I think we are running a little bit out of time. Just summary. So what I showed today is a concept of real-time machine learning and real-time features. And I shared what are those challenges to build this real-time machine learning system. And there's tools you can use, like different tools for you to build this system. And finally, I show you a case study, a demo. Right? Yeah, that's what I'm going to share today. Thank you.